Hey folks, welcome to Module 2 of the Commercial Software Engineering Accelerator, Machine Learning for Product Quality. For this module, we're going to do a dive into the design and architecture of the solution. First, we're going to start off with some key design considerations. We talked a little bit about this in the issues section during the introduction module, and that we're going to address a few of these. The first one being cost. The selection of a lot of the components were based on their availability of auto turn on, turn off capabilities. What I'm going to term quote unquote elastic charge. What that basically means is that it'll charge based on amount of usage. And then also automation. There's a fair amount of automation involved in this, and that helps reduce the amount of time that a worker has to spend doing things. So like deploying to web applications, if you're deploying a variety of services, being able to just check in code and it automatically deploy reduces the amount of time necessary for that worker to spend flipping between tasks and focus more on feature development. Skills required, I tried to narrow this down to just two. The more skills you add and the more things that you add that people need to know, the more it costs to maintain the solution. So in this case, we've stuck to just Python and JavaScript. Absolutely everything is built with those two things and a little bit of SQL, but not really that much, very minimal SQL. Scalability, all the components chosen dynamically scale up and down and theoretically to infinity and beyond. So now with that, there's things that you may have to do to get extra scalability, like in Event Hub, it can scale, quite large. However, you have to start taking advantage of partitions and consumer groups. So although the architecture has those pieces in place, you need to actually leverage those capabilities. And then finally, security was an aspect that we talked about, and being able to move through the various environments. So there's a key vault that maintains all the secrets, passwords to the database, access to the data lake, all these things that you need to know to get access to the data and the resources. That's all being held in key vault, and then being dynamically loaded into the various components as environment variables, and then control over the data and the key vault and the DevOps pipelines is all via RBAC controls. So that helps achieve a fair amount of at least that layer of security. So this is what the architecture basically looks like. This is the current architecture. I'm going to talk about a better architecture. So this is what currently exists, and we'll be moving it towards the next architecture. And when I show the next one up, we'll talk about what are the advantages of that. So here what we have on the top is the actual components that are the data flows, and on the bottom are a lot of key supporting type capabilities. So we'll start with the key supporting capabilities and talk about what those do. Private PyPy, what this basically is a packaging index. So if I create Python code and I want to distribute that as a code package, I need to have a place to do that. But if you upload it to the publicly available one, you're releasing your intellectual property to the world. So having a private one that requires a key to access is a big advantage. So I wanted to make sure that we could demonstrate how do you actually create one of these packages and distribute it for an environment like this. And the key reason we're wanting to do that is we have things like connectors, data models, data generation, machine learning that all needs to get distributed. And it was really nice in this project that when we did that, I would have discovered an issue in, say, the web application. And because it was taking a dependency on that common piece, when I fixed it in the common piece, not only did it fix the web application, it didn't fix the machine learning prediction application, it also fixed the data generator, and it fixed the machine learning explore and train. So that's really a nice thing is when you find an issue, you fix it once, you write a test against it, improve your code coverage, and distribute it through this packaging system, and it just gets distributed and everybody inherits it. Really, really nice. Azure DevOps and Azure Key Vault are being paired together quite a bit, but Key Vault's also being used in other areas. So it's also important to know while we're talking about the DevOps topic that there are multiple environments. Broke that down by resource group. So in this, what we're looking at is this could be my dev resource group. I also have a QA resource group and a prod resource group. And Azure DevOps and Key Vault pair together to not only integrate the code together, things like grabbing the private packages from PyPy and then mixing that with the web application or the prediction application, but also actually releasing it to the dev environment and releasing it to the QA environment and releasing it to the prod environment. That's where the magic between Azure DevOps and Key Vault really come to bear, in that I can link the Key Vaults from the different resource groups to my DevOps pipelines, restrict the scopes of those to a release pipeline. So if I have a release pipeline for dev, just the keys from the dev resource group are available to that. If I have a pipeline for integration or QA, just the keys are available to that. And then Azure DevOps is going to inject those secrets and those keys into the services being deployed in those environments. That way, the dev web application has access to the dev SQL. But without changing any code, the QA and the integration now have access to the QA and the integration SQL and the prod and so forth and so on. So those two pieces there are critical for being able to create a flow between your different environments. The container registry is also another key cross-cutting capability. The data generator is a container instance. The web application is a Linux-based container running on an Azure App Service. And the machine learning model zoo is, well, we're not generating containers for that, but you could. But containers are a nice thing. And in this case, we're using containers for two of the pieces. So that holds our containers in a private location. So not publishing to Docker Hub. I've seen customers accidentally do that. Very, very bad. Remove those from private Docker Hub or from public Docker Hub. Get yourself an Azure Container Registry. You've got keys to protect the download and distribution of those container images. So that's cross-cutting. Even in the better version of the architecture, the cross-cutting components are actually remaining the same. So for the actual flow of the data, the first thing is we have a data generator. For this sample, I don't have 50 factories wired up. I'm a guy sitting in my office, don't have factories. I created a data generator to simulate data, and I'm feeding that into an event hub. IoT Hub is backed by Event Hub, at least right now it is, and that's going to be a very common way to get data in. As of right now, it splits into two ways. We're going to deal with the top path first. So the stream transformation, the big ML explore and train, and the model zoo. So when data is coming in, the first thing that we want to do is be able to transform that data into a more generic format. The reason I'm wanting to transform it into a more generic format is I want to be able to enable an easier process for creating machine learning compatible data. So what that basically does, and what this transformation does, is it takes your data package in your proprietary format, whatever that may be, and it expects three key fields. It wants a metadata field, and you stick whatever you want in there. That's just metadata. My stuff primarily ignores that. You get a features column, which is these are high-level features and capabilities about whatever this thing being manufactured is. And then you get a telemetry field, which is basically a list of multiple variables with timestamp. The stream transformation takes that raw data format and transforms it into this more generic format. And then it drops that generic format into an Azure Data Lake store. It's important to use something like Azure Data Lake Store because just for my simulation and these couple of weeks that it's been running, I'm upwards of 10 million, 20 million records. It's just, and that's not like record per each telemetry, that's individual widgets being sampled. Now, before we move all the way on to actually what the big ML exploration is doing, it's important to note that the stream transformation is converting the data into basically windowed packages. So it's, if you have a data stream that says temperature 10, temperature 15, temperature 17, temperature 18, and each one of those are individual packages being sent up, you're going to need to use what's called a user-defined function to transform it into the generic format, but also you're going to need to do a group in a window. So you'll need to group by whatever the widget serial number is, and you'll need to create a window over time. The key thing about this particular anomaly detection algorithm and what it's focused on is detecting patterns over a window and not individual point anomalies. I think that's a key distinction. There's a lot of solutions out there for individual point-based anomalies, but what I found is that typically there's a pattern over a window that indicates an anomaly in a discrete process, and that's what this does. So if you're setting up just points in time, a key thing that your transformation needs to do is to actually group by the thing being manufactured and then window over some time period for that particular discrete process that you're doing. Once it does that, then it can pipe it over to the data lake, and it just simply drops it for archival. At this point, you can do out-of-band training. So this is kind of the out-of-band, non-real-time portion of the solution. I picked Databricks. Databricks because it's a managed Spark instance. It has a lot of nice things going for it. I can tie it in with the Azure Machine Learning Services. I get RBAC controls. There seems to be a lot of movement and push for Databricks. And it also has multiple clusters, dynamic scale clusters, auto turn on, turn off. I can tie it in with Azure DevOps. There's just a lot of nice things going for it. I can tie it in with Azure Key Vault. I get the DB utils capabilities. I can mount the data lake directly to a cluster. So it was a really great natural selection for doing large machine learning workloads on top of large data sets. So what this really is used for in this solution is an exploration of the data, see what we've got, see if we can figure anything out, transform the data into the machine learning compatible format, and then train some algorithms on it. Now, we'll see when we take a deeper dive into it, the code that does the conversion from the generic format that Stream Analytics drops into the data lake into the machine learning format, it dynamically dissects that generic format and figures out what are your variables in the telemetry stream, what are your features, what are the unique values, and what does it all look like? And it creates the models dynamically that fit that particular data structure. And we'll dive deeper into that in the machine learning section. From there, what it does is it registers the machine learning model into the model zoo. This is the Azure Machine Learning Workspace and Services. It has the ability to store models, model files, and version numbers. This is a way that you can get your machine learning models out of the Databricks world and be able to do other more interesting things with them. Things like put it into an Azure function, put it into a container instance, run it on an IoT edge device. In this case, we're registering it so that we can use it on the real time stream inside of the ML prediction Azure function. So at this point, let's just quickly recap. We go from the data generator to an event hub. The data generator just pushes messages onto the event hub. Stream Analytics transforms that raw feed into a generic format. Databricks stands on top of the data lake, which has a series of these JSON files, grabs those, extracts them, converts it to a machine learning compatible format, trains a machine learning model on it, and then registers that model in the model zoo or the machine learning workspace so that we can use it later. Now moving on to the real time. So the data generator is still producing the same data feed, still goes into Event Hub. We have two consumer groups. One consumer group is in Stream Analytics, consuming from the Event Hub. We also have another consumer group which is baked into a binding in an Azure function. Azure Functions was an interesting choice. It's extremely cost effective. I should have brought up the numbers for what the cost difference actually is. In one case with a customer, and it does depend a lot on how many algorithms you have and how you need to pack them. And there's other caveats and choices that you can make. But you get the first 1 million activations for free, and then I believe it was 20 cents per activation after that. That's as of this moment. So, you have to go to the Azure pricing calculator and verify or talk to your account executive just to get real pricing. But anyways, it was much cheaper than some of the alternatives, primarily because it dynamically scales, and we are able to dynamically load models from it. So you can actually query the model zoo and grab a model file and just have the same endpoint dynamically loading up models. In this case, we have one model. We didn't do the many model scenario, but Azure Functions still ended up being a very cost-effective, dynamically scaling component. So what we ended up doing is in the version control system, it has the models. So there's a script that you run and it downloads the models from the model zoo into the folder structure for the inference function, this machine learning prediction, and then checks those model files into version control, which then gets packaged up by Azure DevOps and then deployed into dev, integration, QA, and prod. So the machine learning prediction basically takes the raw data of the proprietary format straight off of the Event Hub, transforms it into the machine learning expected format, and then creates as an output its predictions. Now, it puts those predictions into two places. It puts both good and bad, whether it was good or bad, whatever it was, it puts that into the SQL database, and it puts the bad predictions. If it sees it's a bad, it puts it both in the SQL database, and the web application has a socket IO server sitting on it, and it hits that socket IO server. Now we're going to talk about in the next phase how there's some caveats associated with this particular section of the architecture. So as of right now, that's what the architecture looks like and does, and some of the reasons behind it. So it's a fairly robust, fairly solid architecture with a few caveats. If you can guess what those are, now would be a good time, because next we're going to go through a few of the issues and how we're going to improve upon it. So here's a slight improvement. This is not what the solution sits like today, but If we see interest in the solution, we'll go back and start revamping some of it to work this way. The key difference between the previous architecture and this one really stems at taking more advantage of stream analytics and stream analytics capabilities to simplify the skills required. So what is happening is, in the previous one, the inference function, the machine learning prediction function, you still had to know how to convert it into the generic format, and then from the generic format into the machine learning format. In this way, what you do is stream analytics transforms the raw format into the generic format for you. So you're coding that only in one place, not two places. And then after it does that transformation, it pumps that into the machine learning prediction as a user-defined function, which then it can pump out to the data lake as well as the web application. Now, to achieve the transformation from the generic format into a machine learning compatible format, that code is going to be distributed by the private Python package. There's not really that much of a difference in how you formulate your data for a set of machine learning algorithms. So for telemetry, there's, it's a certain shape and size. So getting it there is a great thing to be able to distribute, because you'll need that both in your exploration and training as well as your prediction capability. So code once, distribute twice. Another key difference here is you'll see that at the web application, there's an additional service. This is actually a fairly new service, but it's the Signal R service. Distributing socket connections is a challenging task. In the web application, using the Python-based approach with open source libraries that are available, we're using Socket.io. Just when I started experimenting, trying to scale it up to 2, 3, 4 instances of the web application, in a web application with HTTP post response, that seemed to work fine. But scaling a socket connection, it might get hooked up to not the correct instance. So stream analytics might be posting and connecting to one of the instances while the client's connected to a completely different instance. So they're not necessarily communicating together. So there were some concerns and issues around that. Whereas Signal R is a managed service provided by Microsoft that just handles those complexities out of the box for you. So those are the key differences between the current architecture and this improved architecture. If you're going to implement this, I would suggest starting with the current architecture and then making the efforts to migrate to the new architecture. Also, feel free to reach out to myself, and we can discuss, how would you go about implementing this improved architecture over the current architecture. With that concludes the design and architecture component of this module 2, and hopefully you'll stick around for the next few modules.